Hello friends, today we are going to see an interesting application of graph theory, that is Dijkstra's algorithm. This algorithm is used to find shortest path between a vertex, between every pair of vertex, we can say, or you can fix one particular vertex, and from that vertex you find out shortest path between that vertex and every other vertex of the graph. For this, we consider a weighted graph. Now, let me recall what is a weighted graph. A weighted graph is a graph where edges are assigned some numbers. Now, numbers may be the distances along that particular route. So, I'm just drawing a graph. This is a graph A, B, C, D, E, and F with some numbers assigned to every edge. So let us say that these are the weights. These are the distances across all the routes. First of all, this algorithm can be used for a connected graph. So connected graph means every pair of vertices is connected. Now, what do you mean by connected vertices? Connected vertices are the vertices where there is at least one path available. Okay. Now, see, in graph theory, we need to keep backtracking of the concepts. When I say connected graph, I need to understand what is a connected graph. Then I need to understand what are connected vertices. Then I need to understand a path. So basically, it all starts with a walk, right? Walk is an alternating sequence of vertices and edges. And a walk in which there is no repetition of vertices is called as a path. Now, when you get, now let me just define connected vertices. When you see that there exists at least one path between the vertices, they are connected. Okay, I'm saying at least one path. That means there can be more than one path available. Like in this particular graph G, if I want to find out path from A to F, okay, A to F, then there are various paths available. You can have a path from A to B, B to C, C to F. You can have a path from A to B, B to D, D to E, E to F. A to B, B to D, D to C, C to F. And many more are there. Because it has got many circuits, so there are so many alternative paths available. So one needs to find out the shortest path. So this is a very much useful application of Dijkstra's algorithm. One can use it in case of the situations where there are distances. So anywhere where we consider distances in that particular graph, we can apply Dijkstra's algorithm. So let us see what is it. What is Dijkstra's algorithm? So I am considering this particular graph right now only just for showing you the example of weighted graph, but for actual Dijkstra's algorithm, we will consider another graph. Let us have a graph, say, so I'm considering another graph, weighted graph. It is a connected graph, of course, as specified earlier. So there are in all 6 plus 3, 9 vertices. And let us have the vertices as A, B, C, D, E, F, G, H, I, J. Okay, and the distances, let us see the distances. 3, 2, 5, 5, 4, 7, 3, 2, 1, 1, 4, 6, 8, 7. Okay, so I have chosen a graph. Now, in Dijkstra's algorithm, we use a labeling technique. Okay, what is this label? We are going to put the labels and we are going to denote them by lambda. Label for each. So the distances will be labeled as lambdas. So we will be making table every time and step by step we will start it. So the vertex from which you want to find out the shortest path is given to us. So for here, example, in this graph, I am finding out the shortest path from the vertex A. Okay, so for that particular vertex where you are starting, the lambda A value is equal to 0. Okay, so and for other, I want to find out distance between A and B, A and C, A and D, and so on and so forth. So those are right now unknowns to me. So all other values will become infinity. Those are unknown to me. And then later on, we will go replacing them. Okay. So this is the way we prepare the table. First of all, we consider the vertex here. Then we consider the labels. And then we consider T. Okay. So this is the temporary set, one can say. So here I am considering all the vertices. In V, I am writing all my vertices. F, G, H, and I. 4 and 5. Yeah, there are 9 vertices. Now, as I'm starting from the vertex A, the lambda A value is taken as 0 and all other lambda values are infinity. Okay. Now, we will start from A. Here in this set of values, 0 is the minimum value, right? So I'm going to mark it. I'm going to mark 0 here. And then here I will put dash. That means I'm not going to consider A. So naturally, distance between A and itself is 0. So that is the shortest. There is no need actually to find out the shortest path as such. And now we are left with these many vertices. Now, from the vertices which are written in the set T, we will see how many vertices are adjacent with A. So A is adjacent with the vertices say B and E here. Okay. And the weight of AB, that means the distance between AB is 3 and distance between AE is 7. Okay. So A is adjacent with B and E. So we will find out the label of B and E here using the label of A. Okay. So lambda of B, the formula is just a minute. The formula is lambda of B is equal to lambda of A plus weight of the edge AB. Okay. And here it is lambda is 0 and the weight of edge AB is 3 given in the graph. So that is 3 and which is of course less than infinity. So we will replace infinity by 3 in the next table because we are ultimately interested in finding the shortest path. So we should go on choosing the minimum values which are available. Now lambda E also we will calculate along with that. So lambda E will be lambda A plus weight of AE. So that is 0 plus 7, which is equal to 7 and which is again less than infinity. So that also we will replace in the next table. So now we will get the next table as V, lambda V and T. So here I am writing all my vertices A, B, C, D, E, F, G, H, I. Here I am writing 0. Now lambda B is replaced by 3 and lambda E is replaced by 7. All other values remain as infinity because A is not adjacent with them. A is just connected with them. A is not adjacent with them. Now here we had put a dash for the vertex A. So now from T we will find out, from these many numbers we will find out the minimum number, and that is here lambda B is minimum, that is 3. Okay, so we will see now B is adjacent with which vertices. B is adjacent with which vertices from T. So T does not include now A and B. So T is adjacent, B is adjacent with C, D, C and D. So we will find out the lambda values of C and D. So B is, we will write lambda B is minimum, first of all. And B is adjacent with C and D. C and D. Therefore, lambda C is equal to lambda B plus weight of BC. Now, lambda B is 3. And what is the weight of BC? The weight of BC age is 2. And weight of BD age is 5. So this is 5 and 5 is less than infinity. Lambda C was infinity. So we will replace lambda C value by 5. Similarly, lambda D we will write lambda B plus weight of BD, the age BD. So 3 plus 5, that is 8, which is again less than infinity. So we will replace that also from the previous table. Now I have got V, lambda V and T. So lambda V, I am taking A, B, C, D, E, F, G, H, I. All my vertices. Now this is 0, this is 3. Lambda C now we are replacing by 5. Lambda D we are replacing by 8. Lambda E was 7. And the rest values are infinity. Now here, when we have excluded now A and B from T, now lambda C is minimum. And therefore I will put a dash over here. And now in the next table, I will be considering only these 6 vertices in T. So once I put a square, the label becomes fixed. That means simultaneously we can think about the graph also. Okay, so here I'm just making arrangement of drawing the graph simultaneously. We will come back to this page frequently. Let me just draw it quickly. Yeah. So my graph is, okay, this is our graph. A, B, C, D, E, F, G, H, I, and J. I think in the previous table we did not write for J. So let us write for J also. Yeah, here also we did not write J. So for J it is infinity. Now in the next table also I have to consider J. There are 10 vertices. Yeah, correct. So now, see, when right now I'm just looking at this particular table. Okay, the table where I'm putting star. So A to A, the distance is given to be 0. A to B, the distance is given to be 3. A to C, the distance. So these distances are fixed now. Okay. So 0, 3 and 5. So we will draw the graph accordingly. So A to B, the distance is 3. So this is the shortest path from A to B. Then from A to C, this is the shortest path I am getting. Okay. There are so many other paths available you can see, but the shortest among them will be A to B, B to C. So simultaneously, we should be drawing the graph also. Now, we can see lambda C is minimum, right? Now, C is adjacent with which vertices that we want to see? C is adjacent with D and G, okay, from T. D and G from T. So in T, there are A, B, C which are excluded, okay, C itself also. So we can calculate lambda D and lambda G. Now lambda D is already been calculated, but that was using lambda B. So we want to check here whether we can travel from A to D via C instead of some other vertex, okay. So lambda C is minimum. Now lambda D is equal to lambda C plus weight of CD. So lambda C is 5 and weight of CD is, I have not taken it here. So let me define it as 2. Okay, so 2. So it is, the answer is 7 now. And what we were getting here, lambda D was 8. So 7 is less than 8 here. And therefore, I can replace this 8 by 7. Okay, in the next table. Then similarly, I will calculate lambda G. Lambda G is infinity yet. So I can simply replace it with the whatever value I will get. So lambda C plus weight of CG. Lambda C is 5. Now weight of CG is given to be 1. So 5 plus 1 is 6 is less than infinity. So we will replace both of them in the next table. So I'm preparing the next table now. So again, I will be writing V, lambda V and T, A, B, C, D, E, F, G, H, I, J. We have to remember this. Now 0, then 3, 5. Now lambda D I am going to replace by 7. Okay, so 0, 3, 5, 6, 7. And for G it is 6. 0, 3, 5, 6, 7. Then infinity. And then for G, I have got answer 6. Infinity, infinity, infinity. Now A is not there, B is not there, C is not there. Okay. Okay. So now among these vertices, which one is minimum? Now lambda D is also minimum and lambda G is also minimum. That is 6. So you can choose any one of them here. So let us consider D itself. So now we are left with E, F, G, H, I, J. Okay. So lambda D is minimum. D is adjacent with which vertices? Now what happens to our graph here? Let us see that when lambda C was considered and lambda D became 7, lambda G became 6. So in the graph, lambda, see, initially I was getting the path from A to D as A to B, B to D. That was giving me the distance equal to 8. But now when I am considering lambda C, if I travel via C, so A to B it is 3, B to C it is 2, and now I am taking it as 2. So it makes distance equal to 7. So this path is giving better answer. Okay. So 3 plus 2 plus 2. And of course for lambda G it is 6. So it is showing me this is the distance 1. Okay. This is how one can progress the graph also simultaneously. Now lambda D is minimum and D is adjacent with which vertices among T? The vertices which are left in T, from them we have to choose. So D is adjacent with, so ABC we will not consider, D itself we will not consider. D is adjacent with E and F only. Okay. E and F. So we will calculate lambda E as lambda D plus weight of DE and lambda F as lambda D plus weight of DF. So let us see. What is lambda D? Lambda D is 6. And what is weight of DE? Weight of DE is 4. And weight of DF is 5. So this 10 answer, lambda E is 7 actually. And now I'm getting 10. So 10 is greater than 7. So I will not replace it naturally. Okay. That means this is creating a longer route than required. So unnecessary, we will not introduce that route in our answer. So lambda F is equal to 6 plus 5, I guess. Yeah, we have to go back to, yeah, DF. The weight of DF is 5. So it is 11 and lambda F is infinity yet. So 11 is less than infinity naturally. So we will replace it. Okay. So in the graph, what happens now? If I choose this particular age, okay, D to E, for traveling from A to E, it will create distance of 10 units, 3 plus 2 plus 2, 6 plus 4 units, but one should not, we are not recommending that. We are sticking to the previous answer, that is 7, and which is nothing but this route. Okay, A to 7. So we are sticking to this route, which goes directly from A to E, the adjacent vertices. Now, A to F, of course, we will replace. So the next table will be V, lambda V, and T, A, B, C, D, E, F, G, H, I, J. Okay, so this is 0, 3, 5, 6, 7. So we are not changing lambda E, but we are changing lambda F, that is infinity is changed, replaced by 11. Then 6, infinity, infinity, infinity. Then dash, 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 dash. Now, among the vertices, when you exclude now A, B, C, D, you are left with E, F, G, H, I, J. So among those vertices, lambda E, G is minimum. Okay, so you are left with E, F, H, I, J. Now, among E, F, H, I, J, G is adjacent with which vertices that we want to see now. Okay. So we will write here lambda G is minimum. And G is adjacent. Now G is adjacent with which vertices? G is adjacent with F, G is adjacent with H, I, and J. All four vertices. Okay, G is adjacent with F, H, I, J. All of them are still there in T. Okay, F, H, I, J. So let us find out lambda F once again. We want to see whether we can insert G or include G in the path from A to F, A to H, A to I, A to J. Whether G has any significant role in that particular path, that we want to check. So lambda F would be lambda G plus weight of GF. Lambda H is equal to lambda G plus weight of GH. Lambda I equal to lambda G plus weight of GI. Lambda J is equal to lambda G plus weight of GH. Okay, so what is lambda G value here? 6. And now let us see. It is 1, and it is 2 for F and 1 for 8. Okay, so 6 plus 2, 6 plus 1, right? Then 6 plus 4 and 6 plus 8. Now Hij, their lambda values are still infinity, and therefore we will naturally replace, okay, all these lambda values. Now lambda F is becoming 8. And what is it in the previous table? Lambda F is 11. So one should replace it by 8. So 8 is less than 11, and therefore I'm going to replace it. That means if I include G in the path from A to F, that will give me a path with shorter distance or smaller distance than 11. Okay. Earlier, what we were including? Earlier we were getting the answer equal to 11 for F, for the vertex F, because it was due to 3 plus 2, 5, 5 plus 1, 6, 3 plus 2, 5, 5 plus 2, 7, and 7 plus, yeah, how we were getting 11, that we want to check using D and DF. DF was, what was the weight of DF? Yeah, it was so it should become 12 or what? We have taken 7. Why we have taken 7 now? Lambda D 6. How we are getting lambda D 6? No, lambda D is not 6. Lambda D is 7 actually. Lambda D is here, it is 8. Now here it has become 7. Now in the next table, lambda D, how it has become 7. Okay. Sorry, we by mistake we wrote lambda D as 6. It should be written as 7 here. Yeah. Okay, so let us redo this part again. Until here it is correct. Lambda D is 7, and which is less than 8. So we are replacing it. Okay, lambda G also we will replace. Then we are here. Yeah. So we need to replace this. So it should become 7, and lambda E is also 7 already. We are getting lambda E at 7, lambda D also at 7 now, and lambda G is 6. Yes, so let us redo this part, doesn't matter. Okay. So now I was talking about tie. There is no tie right now here. Right now, at this particular stage, there is no tie. Okay. So among the vertices, now D we have to consider over here, and G has got the smallest one. So G I will not consider. Okay. So lambda G is minimum, and G is adjacent with which vertices that we want to see. G is adjacent with which vertices? G is adjacent with F, H, I, J. Okay. F, H, I, J. F, H, I, and G. So here we will be, so we have to erase all this thing. Yeah. So let us go back here and rectify our mistake. So we have now changed lambda D, we have retained to 7. Okay. From 8, it has become now 7. Okay. So now lambda G is minimum. So in my graph also, see 3 plus 2, 1, 5 plus 1, 6. So the path from A to G has the distance, shortest distance equal to 6. The path from A to D, it is 7. Yes. So right now we will calculate lambda of F. Lambda of F is lambda G plus weight of GF. Lambda of H is equal to lambda G plus weight of GH. Lambda I is equal to lambda G plus weight of GI. And lambda J is equal to lambda G plus weight of GJ. Okay, so lambda G is 6. And the weight of GF, weights are 2, 1, 4, 8. So quickly I'm writing it 2, 1, 4, and 8. So all these are less than infinity. Okay, so I'm going to replace them. And this is 8. 8 is less. Now what is lambda F here? Lambda F is infinity. So 8 is also less than infinity. So I'm going to replace it. Okay. So in the next table, let me duplicate the page. Yeah. So next table now, we will replace all of them. So we will replace what all? We will replace lambda F by 8. Yeah, and all Hij also we will replace. Okay. So lambda 8, F will become 8. H is 7. I'm sorry, here 7, then 10, and here it is 14. So 7, 10, and 14 all are less than infinity. Therefore, we will replace them quickly. Okay. Now, next is now we have got 7 3 times. So there is a tie now among lambda values. So we can choose any one of them randomly quickly. So let me choose D, the vertex D with minimum lambda value, and then I will erase this. Okay. So here we are choosing lambda D to be minimum, and D is adjacent with which vertices among E, F, H, I, J. D is adjacent with on E, F, E and F. Okay. So we will see whether we can include D vertex in the path from A to E, A to F. That is what we want to see. So D is adjacent with E and F. So lambda E is equal to lambda D plus weight of DE. Lambda F is equal to lambda D plus weight of DF. So lambda D is 7 plus weight of DE. DE is 4 and DF is 5. So 4 and 7 plus 5. So lambda E is already 7. So 11 will be greater than that. So we will not replace. Don't replace. We keep it as 7. And 7 plus 5, 12. That is also greater than 8. So we will not replace anything. Okay, here. So we are retaining our path from A to E with the 7 length. So where we are getting 7 length, A to E is this. Okay, and A to F as A to F, the distance is 8. So how we are getting 8 here? Let us see. A to F. Yeah, that was A to B, 3 plus 2, 5, 5 plus 1, 6, and 6 plus 2, 8. So this is the path we are getting from A to F right now. Okay, we have not fixed it yet, but I'm just showing you. Okay, so there is no change in this table now. Now next we will be choosing. Now next is now D is gone. Now we will be choosing next 7. 7 is again minimum for the vertex E. So let me choose that vertex E here. Okay. And then we will write. So lambda E is minimum. Now E is adjacent with which vertices? E is adjacent with only, I think, F. Okay. Among the vertices which are there in T right now. So E is adjacent with only F. So lambda F would be lambda E plus weight of EF. That is 7 plus, now weight of EF is 3. So 7 plus 3 is 10, and which is greater than 8. So again, we will not replace this. So right now, so I am understanding here that this answer 8 is giving me the shortest answer. Okay. From A to F, 3 plus 2 plus 1 plus 2. Okay. So now this 7 is gone. Now we will be considering the next 7. So there is no change in this table again. So we are considering the same table. Now next I am going to choose. Now this 7 was included. This is gone. Now next I am going to choose this 7. Okay. And therefore this vertex H is also gone. Okay. So lambda H is minimum. And H is adjacent with which vertices now that we want to see? H is adjacent with I. It is adjacent with G and I. And G and I are there. Only I is there in T. So it is adjacent with I only. So let us see whether we can insert H in the path from A to I. So lambda of I is equal to lambda H plus weight of HI. Lambda H is 7 and weight of HI is 6. Okay. So 7 plus 6 is 13, and which is of course greater than 10. So we will not replace this. Okay. So we will retain with this table again. Okay. Now next time, now as H is gone, now next time, next minimum value after all these 3 times 7 we considered. Now after this, it is the vertex F, which has the smaller value, that is 8. Okay. So we will be writing the same things for F here. Now lambda F is minimum and F is adjacent with which vertices? We want to check, go back and check. F is adjacent with only G. Okay. From T. Because E, D are already been considered. So F is not adjacent with I or J. So F is adjacent, it's not adjacent with any vertex in T. Okay, so we have to go to the next minimum. So that next minimum is now. So this label is fixed. Okay. Now lambda F label is fixed. I showed you in the graph also lambda F label is fixed. Now Hij we are dealing with Hij now. And H label was also got fixed. So when I fixed the H label, the distance was 7. So 3, this is the distance. Okay. This is the distance. 3, 2, 5 plus 1, 6 and 6 plus 1, 7. So this is the path, shortest path from A to H. Now we are left with the shortest path from A to I and A to J. So we have to consider the next minimum, that is 10 here. And then I have to write, I have to find out the label. Okay, so lambda I is minimum and I is adjacent with J, that we can see. I is adjacent with J. So we can find out the label of J using label of I. So weight of Ij. So lambda of I is 10 and plus, let us see what is the weight of Ij. Weight of Ij is 7. So 10 plus 7, which is equal to 17, which is greater than 14. So naturally, we should not replace it. Okay. Obviously, we should not replace this distance. So this is how all our labels are done now. Okay. And the 14th one is minimum. So this is the final table actually. And you can see from G to I and G to J, the distance G to I, A to I, the distance is 10. So how we are getting that 10, that we want to see? 3 plus 2, 5, 5 plus 1, 6 and 6 plus 4, 10. And 3 plus 2, 5 plus 1, 6, 6 plus 8. So this is the answer. Okay. So this is our graph. So I will just show it using the, let me just put, so in the original graph, I will show you that using the red lines. So see, this is our A to B, this is the shortest path. Then A to C, this is the shortest path of 5 distance. Then A to E, this is the shortest path. Okay. Then A to D, the shortest path is 3, A to B, B to C and C to D. Okay, with 7 distance. Then A to F, it is via G. Okay, so these are the, yes. So these red lines, if you see, so this is the graph of the shortest distance. Yeah. See. So this is a very nice application of Dijkstra's algorithm. You can think about a very big graph, okay, where many cities and the routes joining them can be considered, the distances between them will be given to you. But please remember that the graph must be a connected graph when you want to apply Dijkstra's algorithm. Please subscribe our channel GMA for more interesting videos, and do subscribe and do like our videos. Thank you very much. Bye bye.